I started this project, I said to myself that I was either going to get this thing to work, or I was going to die filing. Hey everyone, welcome back to another video. This time I would like to show off my most complex project yet, which was meant to be released at 1000 subscribers and, well, I kinda missed that, but I'm calling it the 1k sub special regardless. As you can see, I named this machine for the occasion. Whether this stands for board filing machine, or big filing machine, or anything else is up to your imagination. But yeah, thanks again for 1000 subs and to the 8,000 that have come since then. So, to begin, I'll say why this is a part 1 of 2. I'll just get this out of the way. It works great, as you will see in a second. I'm really happy with how it turned out. It has ample power and a good range of features that all work well. However, it has one major flaw that means I need to pretty much completely redesign the bottom half. I'll explain what that is later, but I just wanted to put out this disclaimer that while it works well and looks complete, it's still a work in progress, so I would not recommend printing it just yet. In front of you here is my version of a machine that you may not have heard of, called a die filer. A die filer is, put simply, a filing machine. It moves a file up and down through a hole in a work table. But what were die filers made for, and why don't we see them anymore? Well, what they were used for is in the name, filing dies. Dies are a form of tooling used to stamp out and form sheet metal into different shapes. Dies have been around for a long time, with the first example being from 1769. The process has become considerably more advanced since then, but the basic concept is still in use today. There are literally hundreds of thousands, if not millions of products that use stamped sheet metal, as it is a quick and cost-effective way to produce a large number of strong, accurate and identical parts. Die filers were used to provide a clean, finished surface on the inside faces of dies where other forms of tooling would struggle to reach. For some more info, check out the card top left, or look at the reference list in the description. These days, however, die filers are completely obsolete, due to a new technology called EDM. No, not electronic dance music, electrical discharge machining. Specifically wire EDM, the technology uses hair-thin wire charged with electricity to cut through the workpiece. Again, check the card or the description for videos that cover this in much more detail than I could. But yeah, point is that die filers are obsolete from a manufacturing standpoint. For any larger business, a die filer isn't profitable compared to other methods, so they fell out of fashion some time ago. But that doesn't make them useless, especially for a hobbyist. While some operations of a die filer may be able to be performed more efficiently on something like a belt sander, a die filer still has the upper hand in two key areas, those being precision and ability to remove material from the inside of parts, such as turning a round hole square like I'll demonstrate later. So if they're still a useful tool, why not just buy one? Well, the problem here is that die filers are very expensive for what they offer, at least in my experience. Perhaps in the States they are more common, but in Australia, die filers are rare to see for sale at all. And the one I did see crop up was 1.5 grand, which is way out of the budget for many. You can buy kits to make one yourself, but they're just the raw castings to machine one. Not unreasonably priced, and a fun project for sure, but these kits require a well-equipped machine shop to put together, which again is out of reach for many. That's where 3D printing comes in. My goal was to make a competent die filer that could be made with a 3D printer and some hardware store components, apart from the motor. The total cost of this project is around 100 to 120 Australian dollars, of which 60 is the motor. Other costs include around $20 worth of aluminium extrusion and threaded rod, another 15 or so of assorted bolts, 20-ish of bearings, and around a kilogram of filament, which will change cost depending on what brand you use and your infill settings. For reference, I print in literally the cheapest PLA on eBay, so pretty much anything should work. In this cost, I also had a lot of the aluminium, threaded rod, and some bolts left over, and you may already have some stuff lying around, which could reduce the cost. Anyways, with all that background out of the way, let's get into the project. To begin with, the files it can use. I've designed this machine to be able to use a range of common files, but most notably these needle files. I find these at every hardware store and car boot sale I go to. They are practically free, but I found them to be surprisingly versatile. And I presume you can get a higher quality set for more money as well. This set from Audi cost me just $10 Australian for 5 files, all of which could be used in this machine. The holding mechanism in the machine has a 16mm inner diameter, so it can use a file as large as this one here. To use larger files, I change out the holding piece to one accustomed to larger files. To do this, I also change out the middle plate, which is interchangeable to allow for the most ideal support for the file being used. Here's some I've made so far. From left to right, we have a basic small plate for needle files, a large plate for big files, and an elongated plate for small files using the angled table. The next feature of the machine is the ability to tilt the work table at a specific angle. While looking for manuals on older die filers, I took note of this as a common feature and wanted to include it in my machine. I found that the common range seemed to be between 0 and 10 degrees, so that's what I designed this machine to be able to do. Using this knob, the table can be adjusted between 0 and 10 degrees, using this piece here as a reference to determine what the current angle is. Next, I would like to discuss the fence. The fence isn't something I saw on older die filers, but I thought it could be useful, so I decided to experiment with it. Apart from the obvious job of acting as a guide for a long, straight filing operation, I've also found the fence useful as a way to straighten a file while installing it, and to act as something to push off of while filing something. The fence can be easily removed with 2 screws. It could be a bit over-engineered, I do admit, but I think it looks cool, and in the context of a 3D printing project, all these extra gears don't really mean much. There are accommodations for hold downs, pieces that hold down a piece and not make it jump, but currently these are a work in progress. The final 2 features of note are the motor and the file support. The file support can easily move up and down out of the way to make loading a piece over a file more efficient. This system also allows for a variety of file lengths to be more easily used. The motor and drive system is made from a 3000 RPM e-bike motor that is geared down to 300 RPM. This equates to 300 strokes per minute and is in the middle of the range I saw in die filer documentation. Most older filing machines seem to run between 200 to 500 strokes per minute. The motor has a speed control, and I usually don't run it at max speed. Haven't timed it exactly, but it seems to go as low as about 60 strokes per minute while still running reliably. You can use other motors. I was originally using my usual sewing machine motor, but I moved on to this one to make it more easily available for people building. I did have more than a few print failures while building this thing. The most notable being the bed coming loose and causing this body piece to fail catastrophically. So I made sure to clamp the bed down properly and tried again and...
Ah, well hello Timmy, how are you? Yes, hello. You're in a very good mood today. Wow, what a nice day it is. I sure hope that print that I had going for the past 2 days is finished. If that had failed, I would be mighty upset, but you know, the chance of that failing twice in a row is incredibly unlikely, and... Oh yeah, looks like it went just fine. Oh, wait a...
So yeah, it failed 1.4mm from finishing. I'm not mad, why would you say that? I ended up using this one anyways. I reprinted the top 1.4mm and superglued them in place, and that actually works surprisingly well. Anyways, now let's get on to some testing. Test 1 is the most ideal use of a die filer, an operation inside of a workpiece. For this example, I will be making a round hole square, an operation that things like belt sanders or grinders cannot do, making filing really the best option for most people. To begin with, I used a square file to do the majority of the work, aside from the corners. I then changed to a triangular file since it's easier to achieve clean corners, due to only one face being in contact with the workpiece. The end result here is not perfect, but in my defense, I'm using cheap crappy files and there is a camera between myself and the workpiece, so I can't actually see the lines I scribed to cut to. It's not obvious in the video, but the part is also jumping up, so hold downs would help as well. 8 minutes for a hole isn't crazy fast, but it's much faster than I can do. In 4 minutes I couldn't even get one corner done by hand. The second test I'll do is using a large file to do a simple rounding operation, like I showed in the intro. This is real time, it only takes a few seconds to complete the task and produce a good result. The third test will demonstrate both the fence and the angle operation. I'm going to adjust the table to the 10-degree mark, and then adjust the fence to provide the support for this piece that I'm filing. I spend a few minutes filing it, and come out with this result. It's hard to analyze, but by eye it looks very even, and using the precise scientific method of Photoshop, I checked to see the angle and it looks very close to 10 degrees. Could use some work, especially in the measuring department, but I'm still happy with this result. So, it seems pretty successful overall, right? Well, yes, it does work well, but there's one design oversight that means I'm gonna redesign the whole bottom half of this thing. Namely, how grit falls directly onto the workings of the machine. While there is a cover for most of the gears, in its current configuration there really isn't an ideal way to seal off the machine, and this seems like it'll cause inevitable failure. Why I didn't consider this earlier is beyond me, but I didn't, so here we are. I know how I'm going to fix this, but it's going to require the entire bottom half of the machine to be reworked. I'm going to change from my current rotary to linear mechanism to this type shown here. This new mechanism has a few advantages, but most importantly, it is more compact than the current system I am using. This should allow me to properly seal the machine while still maintaining the small form factor. My plan is to use this new mechanism and a set of bellows to seal the inner workings completely from any outside chips. But this is all just planning at this point. We'll see how it actually turns out in the coming weeks. Overall, I'm happy with this machine as an experiment. It has proven the idea has merit, as the machine was rigid and powerful enough to perform well. The issues it has are easy to solve, and I'll be working on them soon in the future. Anyways, that's all I have for this video. If you liked what you saw or anything else on screen now, then maybe consider subscribing and checking out some of my other content. I have many other free 3D printing projects on this channel. Thanks as always for watching, and see you in another video.